Wonderful. All right. We are good to go. Locked and loaded. All right. Really quick, we're going to finish up Freefall. I'm going to take about 10 minutes and talk about this. Going to mention the kinematics equations again. They do change a little bit, but not much. Hopefully you watched the wonderful video on kinematics. I decided just to redo that video. I actually already had it, but I started watching it, and I thought, well, that's from the old book, so chunk it and redo it. So that's what I did, and you can watch over that. And again, I won't ask you on an exam question to regurgitate derivatives and how it's derived, but I could ask you a bonus and ask you, I may give you one of the equations and say, okay, take this equation and either derive it algebraically, graphically, or with integration. And so just look over those, look over that, be familiar with it. You probably don't even need to look over it. You could do it without looking over it. But then again, you might not. So, because this is a little bit different beast. Okay, Freefall. We've already been talking about Freefall and talking about motion, and we've already talked about gravity and how gravity is constant. If any of you went dove hunting Saturday, hopefully you witnessed free fall as birds fell from the sky when you shot them. Unfortunately, we only shot one and about 2.5 boxes of shells. So I couldn't hit the broadside of a barn Saturday. I mean, neither could my son. My son finally hit one. And so they were flying fairly well where we were at. We're going again this Saturday to Jackson County. We're in Talladega County, and we're going to Jackson County. So, but anyway, you kill it and it free falls to the ground. Okay, all right, hopefully. All right. So again, free fall motion, we're just under the influence of gravity. That's the biggest thing to remember. And do we negate air resistance? Well, right now we will. Later on we will look at air resistance and how, when we get into forces and how it plays a role. And we will actually do a lab with coffee filters where we will look at that constant. We will look at the resistivity to motion from a freely falling object. And we'll actually look at that and graph it and see if it follows a square or a v squared or v relationship. It's pretty neat when we look at that, okay? Just using a coffee filter and plotting that motion. All right, but right now we're looking at it without any air resistance. One of the best ways, and they talk about this, to see it is if you take an object and drop it with a strobe light, you can get this kind of effect. You can actually see it, see this kind of effect if you use a strobe light. Now, I do not have one. I wish I did. I think we used to have one years ago, and it went kaput, and we just never did replace it. So, but again, it doesn't have to be a high dollar one. The biggest thing to always remember, come on now. The biggest thing to always remember is that the velocity change is the same each time interval. That's what gives you constant acceleration. Every time interval, typically we do it in seconds, every second, then the velocity change is the same, okay? Typically, when we talk about free fall motion, we say the velocity doubles every second. That's typically how it's understood. And that's just the best way to remember. It doubles every second, okay? Now, of course, Galileo did his famous experiment. Those of you that's already had physics, most of you in here, I think, have had high school physics. You remember Galileo's famous experiment where he took two objects of different mass, a very large stone, a very small one, dropped them from the same height, they hit the ground at the same time. It wasn't until Newton came along, though, and expounded on that and, of course, created calculus. He had to develop calculus to be able to actually properly explain motion and prove motion, and he gets credit for that, and, of course, calculus mostly. And but he actually derived his laws of motion from momentum, not from force. And everyone, he's accredited for his 3 laws of motion, which involve forces, but it's actually derived from momentum, okay? And we'll look at that when we get into force, okay? So, and here that's just talking about how at each each time interval, the velocity is increasing by the same amount. It's constant, okay? All right. Again, neglecting air resistance. Now, if you were to plot this on a graph, looking at an object falling at the same time intervals, if you're throwing the ball upward at 1.35 seconds, and then once it starts to come downward after 1.35 seconds, notice they're about at the same height. They're close, okay? Now, what else can we say about free fall motion? Now, listen very closely to what I'm going to say. We say the velocity doubles, the displacement quadruples approximately, okay? And again, that's why you don't see it's exactly at the same spot, okay? So you throw it up 1.35 seconds later, it's at this position, and then once it reaches its highest position, it says at 1.53 seconds coming downward, it's back at that, almost at that same position, okay? So what are we trying to get out here? And again, we're looking at its constant, or in a sense, symmetrical, okay? There's some symmetry here, okay? And again, if we were to plot that on a distance versus time graph, you see, now of course this is if you were throwing it off the top of a building, if I'm not mistaken, and it was going to hit the ground. But if we're just standing here flat-footed and we throw something up and catch it, then it would stop right here, wouldn't it? Okay. Okay, this is if we're on the top of a building. That's why it's doing that. All right. So if we're here, okay, it'll stop right here. From 0 back to 0. Okay. And then don't forget now what the velocity versus time would look like. Start up here and go this way. Okay. Go negative. Okay. Up and then back down. Okay. So don't forget that. Okay. All right. All right, what about our kinematics? And here they're showing you the velocity, okay, in free fall. Notice it starts becoming negative at this time interval, okay? Why is it becoming negative? Because don't forget your y2, your displacement, your y2 is less than your y1, okay? Therefore, it has to be negative velocity, okay? It's moving downward. And again, how do we know that? Well, because without looking at it in any data, how do we know it's going to be negative? Because it's moving down. Okay? It's moving down. Without looking at any data. Okay? All right. And of course, don't forget at its highest point, where's the velocity going to be? 0. Okay? That would be a good conceptual question for a test, okay? A graph like that. All right, hint, hint, hint. Okay? And I could ask, I might ask you what would the slope of the line be? Would it be constant? Well, that's a real easy question. I might ask you what's the initial velocity right after you release it, approximately. What's the velocity at its highest point on the graph? I might ask you to circle it. I might say circle where the velocity is, where the ball is at its highest point on the graph according to this straight line. Well, you would want to circle right there. Okay, and there's all different kind of ways I can ask it. Okay. All right, any questions about it? Stop. Not going any further, okay? All right, now, so, free fall. Oh, yeah. Ooh. All right. One other thing we don't want to forget. I'm going to add some slides. Why did I do that? Graph slides. Let's look at some problems. Okay? All right, now, the kinematics. What about the kinematics? What happens to the kinematics when we got free fall motion? Well, they're pretty much the same. Page 47, we had our kinematic. Oh, come on. I always forget to turn that pen on. Page 47, we had our 4 kinematics. I actually added one more in the video. I actually added this one, average velocity, and this is one that's common sense. Well, if we take the final plus the initial, or initial plus the final, okay, and divide it by 2. I mean, that one is just an average. I mean, everybody knows how to average stuff. Okay, so you could actually add that one to your kinematics. Okay. Or should it be final? It should be initial plus final. Yeah. All right, let's do it that way. Initial plus final. That's okay. Same difference. All right. Now, all right, but what changes? All right. What changes? Well, when we look at this equation right here, okay, well, we're no longer moving horizontally, we're moving vertically. So it changes to this. Yeah, we're going to have X and Y. Yeah, that's real smart. All right. It's Monday, y'all. I'm going to sling this pen here in a minute. Minus. Okay. So the only change, notice that we changed the variable from X to Y, and we put a negative in there. And of course, this equation, where would it change? We've got this one too. And it would be plus 1/2 V initial plus V final times T. So that one would change to the, what you see what I'm doing? I'm just flipping the y, x's to y's. Now there is a big change right here. Notice I made that negative, and I'll talk about that in a second. All right, and then you've got this one too. V final squared is equal to V initial squared minus 2G delta Y. Okay, now watch. Now this is VF. So in the Y direction, the Y direction, the Y direction. You with me? Y. Velocity in the Y, velocity in the Y, velocity in the Y. Okay, and today hopefully we're going to talk a little bit about, I'm going to assign 3 more problems to all that big pile I've already assigned, and then we're going to talk about which ones we're going to actually grade Wednesday. I'm going to actually call on folks to come up here and work. But you got to have them all done. I want you to try to have all, I'm going to look for all of them, but I'm only going to grade 5. Okay. We're going to look at projectile motion. Well, we're going to look at motion in 2 directions, which will lead into projectile. Now, please pay close attention to that right there. Notice there's G there. And we've already said that G is what? Negative 9.8 meters per second squared. So, when I plug this in, this doesn't mean I say negative. And I may have already said this the other day. No, I only had y'all once last week, didn't I? I think I said this Thursday. That does not mean we say negative. That just means the negative is already added in because of G. Okay? Everybody with me? So when I plug G in right here, I just put 9.8. The negative's already out front. Okay? Please remember that. Don't multiply negative times negative and get positive, because you're going to really, really mess up. The negative's already put in the equation for you. Because G is always negative. It's always downward. It's always downward. Now, what about, and we will work a problem hopefully today for chapter 3. What about when we're just wanting to know how far an object went up, or what was its maximum height? How far did it fall? Can we ever take G and make it positive? Well, yeah, we can. But here again, we got to remember what we're only looking at and what the question's answering. For example, if I'm just wanting to know how high the object is when it stops at its highest path. For that purpose only, we can make G positive because why? Well, why can you do that, Mr. Shields? Because it is above the ground. It's going up. Okay? If we start with initial velocity of 0, it's 0 right here. Throw it up. Okay? Well, everything else goes away and all you're left with is y final. This is 0, that becomes 0, and then all you're left with is negative gt squared. Well, if you work that out, then you're going to get a negative answer. You see what I'm saying? Well, if I'm throwing it up, I'm not going negative. Up is not negative. Up is positive. You follow me? And you probably remember doing these in physics and in physical science. The height equation was 1/2 gt squared, and we made it positive. Y'all remember doing that abbreviated equation just to find height? Probably, okay? 1/2 gt squared. Okay? So we can, again, based on what we're just looking for, we can make G positive in those kinds of circumstances. For any other kind of circumstance, you got to keep it negative. So there's another one of those things you got to keep in your head about physics. Oh me, what are we looking at here? What are we doing? Okay? And we'll work some problems, you'll see what I'm talking about, I hope. Okay? Okay? So remember that. That's one of those another those little trivial things that we can stump our toe on if we're not careful. Because it just makes everything a lot easier. Make it 1/2 gt squared. Period. Okay? And again, we look at inertial reference frame. Where are we starting from? Where are we starting from 0? Or is it negative if we're starting here? Negative and going up to 0. Well, okay. You could look at it that way. And if you looked at it that way, then the negatives are going to cancel out. So it all depends on how you want to look at it. You follow me? I don't want to confuse you. I hope not. All right? Okay. So now we've got some more equations. I know it's too late to each, right? No, hopefully not. All right. Okay? All right. Again, notice nothing changed except the y and the negative signs. Okay? The y and the negative signs. All right. Now, problems. All right. Let's look at some more of these problems. I want to go ahead and add, I think I had you already all the way through 33, problem 33. Let's do 35, 36, and 39. So add problems. Let me go to a clean slide. So we're going to add, what did I say? 35, 36, and 39. 35, 36, and 39. Okay? So we're going to add those to our list. So we got a total of what? 1,000,000. Oh, no, they're not that many. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Ooh, 13, 14. It's a little bit, isn't it? 17. So we got 17 problems total. All right, which ones am I going to grade? What am I going to look for when I grade papers? Well, I want to see all of them at least attempted. Okay, and a legitimate attempt, okay? And a legitimate attempt. All right, I'm going to look at number 35. Number 35 is one that I will grade. That looks like a good problem. What would be another good one that I would like to grade? What was number 33? Number 33, I'm going to grade that one for a grade. So these are the ones that I'm circling that I may call on somebody. You got to get up here and work. All right? Let's see here. What was 21? Yeah. 21 was I think I may look at grading that one. Okay. What was number 17? Is that one with a derivative? Yeah, that one has a derivative. Holy smokes. That's not bad. All right, number 17. Okay. All right, and one more. That's 4, isn't it? Number 17. We didn't do number 7 in here, did we? We did 6. Number 7. All right, now I'm going to grade those 5. okay, for points. But try to attempt all of them. Hopefully you've already been working on them, y'all, okay? Yeah, when I start assigning these things, y'all need to start trying to work on them, okay? Need to start trying to work on them, okay? So you'll turn your papers in, and then I'll get them back to you. This will be Wednesday, okay? This will be Wednesday, all right? All right, okay. All right. Does anyone have any questions? Well, I'll tell you what, let's work one of these, and then we'll take questions, okay? All right. Would y'all like to have a study session Thursday at 10:30? I know that's during break. Or do y'all feel pretty comfortable so far? Or you're just afraid to say anything? Y'all, I'm not going to buy it. Okay. Let me think about it, okay? You want to think about it? Y'all want to have a study session? Study session? All right. Thursday during the break. I know it's only 30 minutes, but hey, it's 30 minutes. All right. So let's plan on probably need to meet in the lecture hall, room 208, just in case I have a lot of people. So let's just plan to meet there at 10:30 sharp, Thursday, okay? 10:30 sharp, because I'm going to offer this to the next class tomorrow, and so, you know, a bunch of them may come, and if we have 25 people, which I don't know that we will, I don't think we will, but we might, then I'll have plenty of room. So let's see, what is Thursday? The 16th? 15th? I need a calendar in here, 15th. All right, so Thursday the 15th, September 15th, we're going to have a study session. All right, study session, all right, at 10:30. I'm writing it down right now, as my daddy would say, okay? All right, good. So we'll meet in the lecture hall, room 208 at 10:30, okay? So bring your problems, bring your notes, anything, and please, any problem you really think you're buffaloed on, that's the ones we really want to try to work, okay? Yeah, the ones you just completely bum-fuzzled on and you just say, man, I don't even know where to start, okay? And if I can give you, and what we can do, we might not work the entire problem, but once we get started on it and you see how it's worked, I think you know how to work it. And then that way we can go to another problem and do the same thing. And, you know, we might can get 4 or 5 problems that way. Okay? All right. Y'all, I promise you, the more of these you work, the easier they get. I'm telling you, because that's physics. That's what I did. That's what everybody does. Okay. And it gets easier. I think probably some of us are still not sure how to interpret the problems. What in the heck is it asking for? Okay. And that's common. So let's work on it. Let's look at some freely falling body. I can't talk today. Freely falling body problems. Since number 36 does not have an answer, you want to work it? Yes. Let's look at number 36. Okay. Is that one of the ones I assigned? No, it's not. But I'll work it anyhow because it might be a good problem. I assigned 35. And 35 is very similar to 36. Yeah, it's almost identical. Okay. So 36, we have a small rock is thrown vertically upward. All right, again, you really need to draw them, okay? And again, I'm not going to get out and shoot points, but you throw a rock, it's thrown up vertically upwards with a speed of 22 meters per second from the edge of the roof of a building, okay? All right. Who built that building? I don't know. It wasn't me. I can build more square than that. All right, now. Well, somebody got crazy on that window. All right, now. Okay. All right. Ah, it's not the edge, though, is it? Here we go. All right, rock. All right, there we go. Okay. From the edge of the roof of a building, and the initial speed was what? 22 meters per second? All right. From the edge of the roof of a building, the building is 30 meters tall, so that distance is 30 meters. Okay. All right. The rock doesn't hit the building on its way back down and lands on the street below. Ignore air resistance. What is the speed of the rock just before it hits the street? Okay? Just before it hits the street. Okay? All right, so let's label what we do know. Okay, let's label what we do know. All right? Now, what else do we know? What's the final velocity of that rock at its highest point? Well, we know it's 0, but now remember, it's not going to stop there. It's going to go on and hit the street, isn't it? So really we're looking for what? We're looking for that velocity right before it hits the street. And everybody in agreement with that? Okay. All right, now, notice this right here. The depth or the height of the building is going to become what? That's y, but now here again, where's our inertial reference frame going to be? Well, where's the dude standing? He's on top of the building, so that means everything below him's got to be what? Negative. Okay? So, the change in y is what? Negative 30 meters. All right, let me go over that again. Did you see what I just did? You see how I drew that little imaginary axis there? Dot, 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 dot. You always need to try to do that in most of these problems. And then think about it. Okay, well, this is where I'm at. I'm the reference point. Whoop. All right. Below me has got to be negative. Okay? It's got to be negative. Below my feet's negative. Look at it on a graph. Sure it is. Okay. All right. What else do we know about this problem that we can write down? Now this is how you need to process these problems in your mind. This is why I'm saying all this stuff and taking the time. Now some of you already know this. It's like, okay, all right, well, you just ride this wave with me, okay? Because some of you may not. Okay. What else do we know? What else is acting on that rock? Gravity. All right. This is how you need to think. This is how you need to try to train your mind. And yes, it is training. Okay? Up, and it's negative, isn't it? Negative. See, this is one, we're not asking how high the rock was when it stopped in its highest point. It's not what we're looking at. Okay. All right. Okay, y'all. Well, we know initial. We know delta y. We know g. Which of our kinematics would this fit? VF squared or VF? All right, we know VF y squared, right? So it's going to fit this kinematic. VF y squared is equal to VF VI y squared minus, now remember the minus is already on the 9.8. Okay? But now remember, that's for the 9.8. So it's 2 times 9.8, but now wait a minute. My distance is what? Remember, that is for the g. My distance is negative 30. Change in y is negative 30. Okay? It's going to work out beautifully. Or you could make it all positive if you wanted to. Because I know some of you are thinking, well, wait a minute, we got negatives under the, well, they're going to go away. So see, you don't have to. All right, see, it all works out. So now we got what? Why did I do that? Good grief. All right. 22 meters per second. So let's take the square root of both sides, square both sides, and we got what? And that's meters per second minus 2 times 9.8 meters per second squared times a negative 30 meters per second squared times a negative 30. And what do we get? We get VFY is equal to what? 32.7 meters per second, 32.7 meters per second. But now wait a minute. Now we got to go back and think about the physics. That's right. It's negative. Right? Everybody see how I did that? Why is it negative, Mr. Shields? Okay, y'all, because it's going down. It passes my feet. It becomes negative. You with me? See, that's not as bad as it seems. You got to write down what you see, what you have, think about look at your equations, and you say, well, how'd you know it was that equation? Well, first of all, we know G is what? Well, it's negative, but it's always going to be what? Constant. So for constant acceleration, we have, well, I actually threw in another kinematic, the average velocity one. You actually have 5, but 4 in your book, but I added one more, which was one that, commonsensical, taking an average, all right? Okay? You had initial velocity, you had change in y, you had gravity. You did not have time. Well, thankfully, we have a kinematic that doesn't have time, and it works perfectly. Yes?
How do you get 32.7? I got 24.7.
Now, let me double check my math here. Oh, yeah. Oh, thank you. Squared. Sorry, thank you. Thank you. Thank you. I knew I was leaving something off. Thank you. Woo. Sorry about that. Yeah, you got to square it. I do that all the time. Oh, he didn't want to do that. All right. All right. Thank you. Thank you. All right. Squared. Okay? Any questions now? So see, that one's not that bad. That would be a good test problem right there. Because it's done. It's not 5 parts long. And it's hard for me to ask you a 5-part question and ask many other questions. I mean, I can and count at 30 points. I don't really want to do that, but I can. All right. You see what I'm going at? All right. Now look, y'all, number 35. Are you listening? Number 35 is very similar. Let's look at number 35. You want to look at number 35? Would that make everybody feel better? All right, let's just look at it. Let's just look at it. If a flea, boy, Heidi, if a flea can jump straight up, all right, I know some of you, how are you going to draw a flea? All right, here we go. Okay, flea, there we go. Flea can jump straight up. All right, here's Rover. Okay, all right, he's trying to find Rover. All right, oh, forgot the tail. Bobtail dog. All right, now, there we go. It could have been Kitty, Fluffy. All right, now. All right. Okay. All right, flea can jump straight up to a height of 0.44 meters. What is its initial speed as it leaves the ground? Okay, y'all. What kinematic am I going to use to find that? Hint, hint. Is there time mentioned? We know G, don't we? Negative 9.8 meters per second squared. We already know that. The height was what? Well, y, change in y was what? 0. What? 44 meters. All right. And we want to know what? What was its initial velocity? So VI is in question. What's V final going to be in the y? It's got to be 0, isn't it? Because when you reach your highest point, you do what momentarily? You stop. Okay. Right? Okay. Hint, hint, hint. There's no time in this problem, so which kinematic is going to work? The one we just did, right? Yeah. Yeah. So this one. VFY squared is equal to VIY squared minus. Now let me say this. We can make that plus 2a delta y, but you got to remember that G is negative. So you can write it that way, but you just got to remember G is negative. Okay? You got to remember G is negative. So we can say plus 2a delta y. A is G, acceleration. So we can write it that way. But remember G is negative. So if you write it that way, remember G is negative. Okay? So I'm going to go ahead and write it that way. All right, now. Okay, now on this one, you've got to pay close attention to your math. Because now we're solving for VI. This is 0. What does VI become, sign-wise, when we work the math out? It has to become what? Negative. And guess what we get? We get a what? Now, hold that thought 1 second. I know some of you are thinking, well, when I square a negative, it becomes positive. I've still got a negative because there's in the negatives in the G. It's this. Are you watching? It becomes VIY. Right? Because if it doesn't, watch now, if I do it the other way, I get rid of the negative, look what I have over here. And see, now my negatives don't cancel out and you get a what velocity? You get a negative velocity, don't you? Well, now hang on a minute. Now see y'all, now listen, I'm trying to teach y'all the tricks, and I hate to call it tricks. I hate to call it tricks. But now watch. Look. All right, is negative up? Negative velocity. I got it, thanks. Negative's not that way. If my inertial reference frame is right here, that's positive. Now, if my inertial reference frame is up here, well then, yeah, it's still actually positive because it's going up. So, but that wouldn't make any sense, would it? Inertial reference frame's here and go on. No. You start from where your motion begins. Right? It's those little things, y'all. It's the little things. Okay? I know I'm really stressing these, but y'all, I'm telling you, I did have a good professor. He was great, but I sometimes I didn't listen to those little things, and I got buffaloed, and I'm like, holy cow, where's this coming from? So it's the little things. So all right, what do we get? We end up getting a 2.94, don't we? All right, so the initial velocity was 2.94 meters per second. All right, now, what about B part? It wants to know the time. All right, now we want to find the time. Well, we found the initial velocity, didn't we? The final velocity is still 0. It says what? How long did it what? How long was it in the air? Now, there's two ways we can work this. You with me? There's two ways. We can use that very same equation and solve for t using our VI, what we just found, or use 1/2 GT squared and do what? Solve for time and do what with that time? Double it. Very good. Very good. Right? Do y'all remember doing that in high school? Been a while? See, look, y'all, watch. No, I'm sorry. Why did I say use that same equation? There's no time in that other equation. B, we use this equation. We get what? And now watch what I'm fixing to do. Remember, I said you could do this. Because what is y final minus y initial? change in y. So v y final equals y initial. Well, move the y initial to the other side, subtract it, and you get that. vi t minus 1/2, and this is y now, gt squared. All right, now watch. Okay? Now let's solve for time. Well, okay, y'all, what's change in y going to be? That's to the height. Change in y. If you're going all the way up and coming all the way back down, what does delta y become? 0. Very good. So that term's gone. Now solve for t. Well, watch what happens. It becomes negative VIT is equal to negative 1/2 GT squared. Divide both sides by t, right? And then multiply both sides. Well, we don't really have to. The negatives will cancel out. And then it becomes what? Time is equal to what? I'm going to go ahead and divide through. The negatives cancel out. It becomes what? 2VI over what? G, right? Is that right? Y'all double check my math now. Yeah. Yeah. You see what I did? I divided by t. The negatives cancel out when you divide negative 1/2 G into negative VI. It cancels out. Everybody concur? Now look, I don't have to double the time. But if you don't like doing that and you remember your high school physics, watch, you remember your high school physics, y, or height, delta y, or it was also written this way, h for height, was 1/2 GT squared. And where the heck does that come from? Watch, y'all. It comes from this stinking equation right here. We start with initial velocity of 0. That term is gone. Change in y, okay? You said, well, what happens to the negative? We get rid of it. All right? And how do we do that? Well, because we say the height, we say it's going up, so we have to make it positive. If we just want to know the height, it has to be positive because it's going up. And so we fudge and make G positive there. That's where it comes from. Okay? It's really not fudging, it's just physics. Okay? But if you use that equation, remember what you got to do when you get that time, you got to do what? Times 2. But if you use your kinematics, look, you don't have to times it times 2. All right, now what was your question? I'm sorry. Answer? Answer? Okay. Answer was 0.6. 0.6, is that what everybody got? So part B, the time was 0.6 seconds. Now what did I plug in for VI? 2.94. Okay? Everybody concur on that? Yes? All right, so see, I told you there's more than one way to work these. But now, here again, if you use that equation, remember that's how long it takes to go up here, solving for t. Square. Solve for t. But that's for it to go up here. Then to go all the way back down, you got to double that number when you get it. So you can work this way or that way. Now, y'all, let me tell you something. I know what some of y'all are thinking. Oh, my God, we're going to have 55 million equations. No. You're going to have 5. 5x and 5y. Okay? Really, you only got 5, period. And just remember that the y's, you change it to y, and where it's acceleration, you change it to negative g. So it's really all you got. The rest of this, y'all, is algebra. Right? Why in the world would you say, okay, to solve for that, to do this, and da, 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 da. No. You got 5 equations. Remember your algebra. Because I'm telling you right now, if you try to make an equation for each little situation, you're going to have a sheet of equations this long, and you're going to waste more time trying to find the right equation, and you're not going to finish the test. Okay? Don't do that. Now, if you just absolutely, that's the only way you think you can work them, okay, more power to you. But y'all, I didn't. And I'm not trying to brag. Please don't take it that way. But y'all, we got to where we worked so many of these problems, I didn't need the kinematics sheet. I didn't need them because they were in my head. They were just there. I'm like, oh yeah, it's this. You know? I mean, when you work them, they're in your head. I mean, they really are. You don't even need a cheat sheet. They really are. Now, even when you get into electromagnetism, a lot of that, once it gets there, it's there. Okay. And again, I'm not blowing a bugle, but I'm just saying, you work enough of them, they get in your head. All right? All right. All right, any questions? You want me to work any of those previous problems that y'all are buffaloed on real quick? Number 31. Yeah, because I do want to try to spend a little bit of time on chapter 3. All right. All right. Number 31. Okay. Okay, we got 31. It says the figure 2.31 shows the velocity of a motorcycle police officer plotted as a function of time. Find the instantaneous acceleration at time 3 seconds, time 7 seconds, and time 11 seconds. All right, so we got to find the, what does it say, instantaneous acceleration. So we want to find the acceleration as the limit t approaches 0. And so we know that's dv over dt, right? But we don't have a function, do we? Okay? All right, so now here we have to graphically look at it, okay? So we look at our graph, and our graph looks something like this. And I think it comes over here at 20. This is 20. And this is in meters per second. And the time is down here, time, this is seconds. So we come over here, it's supposed to be flat at 20. And then at about what? At 5 seconds, it goes up, don't it? And it goes all the way up to what? 45? And that's 45, right? All right. And that 45 occurs at what time interval? 9 seconds. So here's 9 seconds, right? All right. And then it goes down to what? About 13? To about 13 seconds. Okay. All right. Okay. All right, so we got to find the instantaneous acceleration. All right, remember, if we're not given a function, how do we find the instantaneous acceleration? It's the slope of the straight line. Slope of the straight line, okay? All right, so what points do we have to choose, okay? All right, well, our time interval for the first one, all right, now the first one at 3 seconds, what's the acceleration, y'all? Because 3 seconds is like what, right back here? Yeah, 3 seconds is right here. So at time 3 seconds, it's what? Acceleration is what? 0, because it's a flat line, right? So that's just reading the graph. It's a flat line, velocity's not changing. But now at time 7 seconds, time 7 seconds. Okay, the acceleration is what? Okay, at time 7 seconds, which is going to be right about, it's going to be somewhere right in here, okay? Okay, remember, there's my point. That's my point right there. But now remember, we got to take the slope of that line. Okay? All right? Well, let's do that. So the slope of that line is what? 45 minus 20? Where does it peak out at? 45 meters per second, right? So the acceleration by definition, is what? Delta V over delta T. Well, y'all, that's the slope of a line. Slope of this graph. Because delta V is on the Y and time is on the X. So we're going to say 45 meters per second minus 20, because right here is our first point. All right, and our times is what? Well, that was at 9 seconds, and this started at 5 seconds. Okay, and so we get an answer of, oh, phooey, 6.3, yeah, approximately, meters per second. Does everybody agree with that? You see how I did that now? Now, y'all, I'm probably not going to, interpolating from a graph is, unless it's extremely clear. I mean, it's a good question, but again, you have to really think about what you're doing. And you better make sure you're, because I think some of you might have wanted to start at 7 seconds. Well, now, let me ask you something. Now, see, again, here's where we get into physically graphing and why I think it's important. We don't do a lot of it anymore. You don't start where the point is. That point is on about halfway up on the slope almost. You start way down here and way up here. You take a broad sample of data. See, you don't start at 7 seconds. You start down here at 5, where you started collecting data. And you end at 9 seconds where it changed and went down. Okay? And I think, again, that's where the old way of graphing comes in handy, physically graphing it by hand. All right, now let's look at the next one. What was the next one? 11 seconds. And then the time at 11 seconds, well, 11, crazy. Time at 11 seconds, the acceleration is what? Well, we do the same thing. When we look at 11 seconds, well, look, 11 falls where? Somewhere right in here. So we got to do what? And it goes all the way to 0, right? Yeah, this is 0. So we got 0 minus 45 over what? The time was 13 minus 9. And we get a what? Negative 11.2. Is that right? Negative. And that's squared. Yeah? Okay. All right. Okay? Can you do that now? All right, do you think you can do the next part? The next part, part B, everybody watch. You're going to use what? Of course, that's in the X. Right? And read the graph. All right, it says in the what? The first 5 seconds? No. Well, no. All right, first. All right. Oh, phooey. All right, how far does a police officer go in the first 5 seconds? Well, his initial velocity is what? Okay. Well, his initial displacement is what? I almost forgot that. What's his initial displacement? All right, look at the line. All right. Initial displacement is 0. Then we got what? 20 meters per second times what? 5. The acceleration is what? 0. And so we get 100 meters. Now guess what you do for the next leg? Times 7 seconds. All right, you ready? Watch. Y'all already got this worked out? Now what's my initial displacement? All right, I've already displaced how many meters? 100 meters plus initial velocity is what? Was it 7 seconds or 9 seconds? Oh, I'm sorry, 9 seconds. Okay, thank you. 9 seconds. Okay. All right, what's my velocity? Well, my initial velocity is what? 20 meters per second. But now, wait a minute. What's the change in time interval? From 5 to 9 is how many seconds? Say, yeah, we got to watch that. It's not 9 seconds. It's the change from 5 to 9. Plus 1/2. Acceleration at that time was 6 point what? Was it 6.25, 6.3? I think it's 6.3 times 4 squared. And we get a final of what? 230? Is that right? And then we do it for what? 13 seconds? All right, well, guess what? Do I even need to do it? What's my initial displacement going to be? 230. I'm putting y'all to sleep, right? No? Oh, okay, good. Oh, maybe. Sort of. Hopefully not. All right, now, wait a minute. What's my initial velocity here? It's not 20 anymore. 45. How'd you get that? Look at the graph. Look at where you start at 9 seconds. You're at 45. Okay? Now, what's the change in time? Well, 9 to 13 is what? 4 seconds. And y'all, let me tell you something. Positive time, difference in time is always going to be positive. It's got to be. Time is moving forward. It is not moving backward. Okay? Time does not move backward. Okay? Motion can move backwards, but time doesn't. Okay. Plus 1/2. And then what was 11.2? Yes. Yes, we do. Thank you. Times 4 squared. Negative 11.2. And we get what? 320. Everybody see how we did that? Now, does that make physical sense? Well, okay, y'all. We got a negative acceleration, so what does that mean we were doing? Slowing down. So our displacement was doing what? The amount of displacement per time interval was increasing or decreasing? If it's negative, if we're slowing down, that means every time interval that elapses, the amount of distance that we cover is doing what? Yeah, because look, y'all, in 4 seconds time, y'all, look how far we went. All right, going forward, we went 130 more meters. In 4 seconds time, we went how many meters? 90? You see what I'm saying? Does that make sense? You see what I'm saying? I want y'all to look at problems and think about what's going on physically. We're slowing down. We're not covering as much distance, displacement. We have to be, y'all, because negative acceleration is going negative. So we're slowing down. So that means for every second of time, our displacement is decreasing. Okay. Okay, that means the distance between you and wherever you're headed is getting shorter. Okay. All right. Okay. That's a good problem. All right. Would I put one like that on the test? I don't know. Probably not. It's a little bit time consuming. I mean, I can't leave all the hard ones off, but that one's really not hard. You just got to interpolate. You got to look at that graph and make sure you read it right. Okay. All right. We good? Yes. Number 9? Okay. Yeah, that's another one of those graphs, isn't it? Let me add some slides. All right. Let's see. Right there. All right. There's really not a whole lot of lecture, per se, content in Chapter 3. It's kind of just adding to what we've already done in 1 and 2 and putting them together. And we're going to look at the vector aspect of it, and we're going to be doing a lot of the square root of the squares and arctangent. Okay? So there's really not a whole lot of... We are going to talk about the symmetry of projectile motion and the difference in x and y and how the objects have different velocities and accelerations, but it's not a whole lot of lecture. It's not a lot of lecture, okay? All right. What'd you say, number 9? This is another one of those, it's a graph, right? Yeah. All right, so number 9. Okay. All right. It says a ball moves in a straight line on the x-axis. The graph shows this ball's velocity as a function of time. What are the ball's average speed and average velocity during the first 3 seconds? Okay. All right, so we have a graph that looks something like this right here. I'm going to try to draw it. It comes out to what, 2 seconds, and then does this, and then does something like that. Okay, so this is what, 2 meters per second? And then this is what? That's 3 meters per second. And what is this right here? This is 1 second. This is what, 2 seconds? Is that right? And then where are we at right here? I'm gonna erase a little of that. I drew it too long. Oh no! Look about right, yeah. And that's 3 seconds. Fairly symmetrical graph. All right, now. All right. So we got to find what? What are the ball's average speed and average velocity? Okay, average speed and average velocity. Okay, well, first of all, we got to determine what? Well, we noticed from here to here, notice that, and this is speed and this is time in seconds. Okay. Notice that it's flat right here. The velocity's flat, and the velocity's flat right here. So notice that acceleration would be what? 0. Okay. So how do we find our what's the first thing? Ball's average speed. All right. Now remember, there's a difference in speed and velocity. Speed is the total distance traveled divided by the total time of travel. We don't give a rip about direction, right? We don't care about direction. All right. However, velocity deals with direction. All right. So let's find our average speed. Well, how are we going to do that? Well, we know that using the equation, we got to find how, first of all, how much distance did we displace? Okay. All right. Now this is part A, right? Part A. How much distance did we displace? All right. Well, look, during this first time interval of 2 seconds, we had a speed of 2 meters per second, 2 seconds, so we traveled 4 meters. During the next time interval, we had a speed of 3 meters per second. For how long? 1 second? Yeah. So what is x total? 7 meters. And what is the total time? From beginning to end. How many seconds total? 3. So our speed would be what? And actually, I'm going to write it this way. We can say speed is equal to the change or the total distance divided by the total time. 7 meters divided by what? 3 seconds. And we get what? 2.33?
Yes.
Okay. All right, now. All right, but what about our average speed? I think that's what it's asking for, isn't it? Excuse me, average velocity. Okay, y'all. Are there any difference? Did we turn the car around? The only thing we did was do what? Boom, boom. We increased in a, what? In a moment of time, literally, boom, went from 2 to 3, didn't we? So our average velocity and our average speed is going to be the same thing. Because why? Because the total distance, the change in the distance versus the change in the time is the same. So we get the same, okay? It's still 7 meters. We started at what? 0 meters and traveled 7 during a time interval of what? 3 seconds. So this is one in which the velocity, this is almost a trick question, is the same thing. They are the same. Okay? They are the same on this one. Okay? All right. And if I'm going to give you one like that, I'm going to give you one that's obvious. There's obviously going to be a difference where you're changing direction. You know, you go up and then down and then over and then back up. If I'm going to give you one like that, if I'm going to give you a problem like that, I'm going to give you one where there's going to be an obvious difference in speed and velocity. Speed is the total distance traveled divided by the total time of travel. Okay? I'm not going to give you one like that. I'm going to give you one where there's an obvious difference in the two. Okay? All right. Okay, now what was the B part? We may have already answered that. Suppose the ball moved in such a way that the graph segment after 2 seconds, was negative 3 meters per second. Now see, that's the thing. Notice that the velocities were all positive too. All right, so let's look at B. All right. Right? So, let me make sure I read it right. Suppose the ball in such a way that the graph segment after 2 seconds was negative 3 instead of positive 3. Find the ball's average speed and average velocity. Okay. All right, well, let me ask you something. Is the average speed going to change? No. Because the amount of distance traveled would still be the same. However, the average speed would be what? All right, well, let's look at this. We know that what? The first leg of the journey was what? 2 meters per second times what? 2, which is 4 meters. All right, but now wait a minute. What about the last leg? Negative 3 times, 1 second. And we get negative 3. Okay? All right. So, speed's going to be the same because it's total distance. We don't look at sign. Yeah, 2.33. However, velocity average, well, it's going to be what? 4 minus 3 over what? How many seconds was it? 3 seconds? And we get an answer of 0.33. The change in x. Actually, I wrote that wrong. I wrote it wrong. Well, 3 minus, yeah. Yeah, that's right, yeah. 4 minus 3. Well, it's going to come out, yeah. Yeah, that's right. Yeah. Okay. Yeah. My bad. Okay. Okay? Because if you turn around and come back, instead of going this way, we're going this way. Okay? So it's 0.33. Okay. All right. We worked a few more problems, but that's good. Any questions on that? Okay? And again, I derived that. How'd I get the... well, excuse me. I should have written it this way. One. There we go. Same difference. Okay. Okay? All right. Okay? And again, what you could do there is add those up and divide by 2. Should work too. You should still get 0.33. What was our velocity? 2 point? No. Because you get 1, you add those up. 2, negative 3, be negative. You're going to get 1. No, that won't work. That won't work. 3. You divide by 3. Okay. All right, any other questions? All right, and that one, again, that one really makes you stop and think because we reverse direction, okay, and that changes our overall average velocity. Now, again, if I give you one like this on the test, this is what I'm going to do. Look, I'm going to go, out, say 3 meters and then up, 5 meters and then, over and then maybe back down. Where it's obvious there's changing direction, okay? That one there was a little bit, you had to really make sure you was paying attention, which, it's a good problem, but still, I want it obvious, okay? All right? You should be able to look at it, though. All right, if y'all don't have any other questions, all right, now, let me, hang on a minute.